I'm Goran Cvijanović, coming from Reversing Labs company, which is IT security company, and we are working in migration of our existing database system to Scylla. Now it is in production for one of our APIs, which handle a lot of requests, and I will show in my presentation some settings and some solutions we tested and put it in production. So a few tricks and a few interesting stuff, how to configure Scylla and how to size it. And I hope you will enjoy my presentation. I'm Goran Cvijanović. I'm software architect in the Reversing Labs company. Here's come back. Here's a little bit about my history. So you will see some 20 plus or whatever it is. Actually, these days is 40 years until I touched my first computer. Yeah, a lot of stuff during these days. I will open this talk with a services overview, just to introduce a little bit what we are doing and what it's all about. So it is file reputation. And before I start, I would like to explain something about reputation. So I asked Scylla support to help me. So I will ask you a few questions. One is, who's here is dog people? Just raise your hand. Nice. Few? Come on, dog people, come on. Come on, don't be shy. Great, great. You will get stickers, badges, something with a nasty dog on it. You will see what is it. It is one of the malware, very famous. After that, who's cats people? You know, dogs and cats. Great, 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 great. Come on, rise up, rise up. I have surprise for you also. There is a nasty malware with cats also, not only dogs. The third question is there anybody have pets which are not dog or cat? Raise hand. Yeah. Fish? No. Raise your hand, raise your hand. We have gifts for you also. It is a reverse pen. Reversing Labs pen. Okay, okay. So the rest of you doesn't have pets, or I will say we don't know. It is unknown for us. So this is the same thing with reputation. So we have Titanium Cloud Reputation Service, which is a powerful threat intelligence solution with up-to-date threats classification and rich content about threats and the files. So it is over 20 billion goodware and malware files in our system. And classification is all about, I've shown you before. So somebody is goodware, let's say dog people, and malware, let's say cat people, and we have also reputation as suspicious. So those are, they have pets, but who knows? And the rest is unknown. But we know it exists. We know that people exist, but don't know the reputation of them. That's 20 and 10 billion. We have information about 20 billion, but we have reputation for 10 billion. Half of them, we know exactly the reputation of that file. And here on the slide, you will see left side, which is our processing engines. We have 4 different processing engines. We have harvesting system, which collects files. We have file decomposition system, which is our in-house proprietary system. It is Titanium Core system, which decompresses files, static analysis over that, and give us a lot of metadata information about files. We have dynamic analysis results, So the static analysis is doing statically analyze file mean does not execute really file, but reverse engineer it. So that is reversing labs all about. Dynamic is actually executing in a secure environment and try to find what that file actually do. It is slow. It can take minutes, maybe hours to finish. And we also use detection rules from more than 40 antivirus companies. They are our partners, so we collect all of that together and classify the file. We have to store that somewhere. We use high available database system and keep the data about reputation and some other metadata about files. And on the red side, there is our APIs and feeds, and the system for upload and download files. And those are used by our end users. So I always said and compared our database and storage. We have storage. We actually store the files. We have more than 5 petabytes of files stored. We have biggest collection of malware files. It is more than 1 billion malware files. I always compare that with a famous movie, Ghostbusters, you know. They have a storage. They don't have additional security over it, and someone shut off the power lines, and all that goes out, all the nasty creatures. We have similar here. If that nasty goes out, but it's always generating new ones during the days, and I said, who are you gonna call? You know, yeah, you will call our APIs. We have 50 plus APIs and feeds, and we preempt emerging threats by monitoring malware in the wild, and using specific feeds that include ransomware, APT, CVE, financial, retail, whatever. We call that verticals. So if you are in a banking sector, you are very interesting about malicious files which can appear in your system, which are targeting your sector specifically. So you buy a feed which we prepare for your specific vertical. So you don't have to worry about some other stuff which may not attack your vertical and your business. We also support advanced search and targeting queries on a large sample data set we have. So it is all about files, formats, antiviruses, privacy, and good weather malware in our cloud service. Now, I go back to databases. We have in-house database, which is actually built 7 years ago. It is distributed key value store, highly available. We want to be able to insert an updates and read a large amount of data with very low latency, stable response time. So we developed that clustered distributed system in C++ based on LSM3 architecture. We have about 3 billion reads, 1 billion writes per day. Latency in database system less than 2 milliseconds, and the latency for our API is less than 60 milliseconds. So it is very efficient. And when we started to talk with the Scylla, they are surprised you have very, very good database. Never saw something like that, but at the end, you will hear what we did. Requirements for database independency is one of things we actually do. We are not migrating from one database to other. We built a database independent layer, something similar presented in previous presentation. So we did data independent layer in our system, connected to all our services, and now we are able to query any database behind. So, but we have our legacy database, which is very good and very performant. So the requirements is that When we migrate, we don't want it to change layer, which is application layer. So things have to be the same. We are based on the key value native protobuf format. We use LZ4 compression to reduce storage size. We need latency less than 2 milliseconds, if it is possible. But the main thing which diverts databases is the support of the record size. We have records which are very different in size. It can be from 1K to 500 megabytes. It's very large. So it is hard to find the database which can support all of that. We are supporting that in our database. And we need, of course, high availability and replication to be on the safe side. So it then appears ScyllaDB. We didn't find in early days nothing that can support that. We started with, for our final, we started with version 2, but after that, when version 3 appears with the MC storage format, we repeated all our tests and tried to figure out if that can fit our use case. So we tested with different config sets, PowerUp POC, and successfully implemented Scylla with 8-node cluster for our largest volume APIs. Concerns we had, I think most of you are thinking about how Scylla performs in a standard modeled way, recommended. But sometimes when you have a lot of data, as we have, we want to squeeze the most from the database system and not to waste precious disk space. So the concerns were the binary key value structure. We are dealing with the protobufs and the binary structures, not text structures. So the chunk size, how we can tune a little bit underneath with the chunk size. I don't know if anybody plays with that. I didn't hear anybody mention that. And about repairs. Everybody talking about repairs, so it is the same. Scylla implementation on our side was successful. We tweaked a little bit parameters, mostly the parameters about supporting the size of the record. So it had to be tuned because defaults are for smaller size of the rows. And we resolved all our concerns. So binary key value structure, it is already mentioned that people are using for the values blobs. So it is easy part, but we are using for key. That is a hard time to get info about that. So that's why I'm presenting here. So the blobs for keys are working okay. And they save space for us almost 2 times. Chunk size also can be adjusted. Version 2 have different default value. Version 3 have now 4K, and 4K is for small records perfect, but for large records, it is better to go with 64K. We achieved improvement in compression almost half with that. Repairs. So the Kiwi use case, we're not doing repairs at all. We take the same approach, almost. For insert updates, we use consistency level quorum. For reads, also. There is some small penalty in the latency for that, but it is not problematic. And for deletes, we use consistency level all. We have all our deletes. We keep all the records all the time, almost. When something goes wrong, we have to delete, but it is controllable. So we use specific consistency level all process to delete records, and then we are on safe side. We don't do repairs. There is the smaller data sets we have in Scylla, and we do repairs specifically for dead key spaces, and it works fine. What is the amount of data we have there? So serving thread classification and rich content for 20 billion. In cluster, I have a small graph here with a daily distribution of the requests. It is about 300 to 400 million requests per day. At the peak time, it is about 20 to 25 million per hour. And how it reflects that to our performance. We did some tests before we were in the production. It is a tool for performance testing called Torus. Maybe you are familiar with that. Very flexible, easy to set up, and these are the results. So the performance test on API includes complete workflow. It is not only database. I will show later also for database what was all about. We fired 32 workers in parallel with 300 requests per second. All the workflow is user request, user authorization, request validation, query database, format response, sending response back, and those are the results. We are in 100% time under 300 milliseconds. It is network latency, everything. When you look at the average, it is 120 milliseconds for response to our end user, which is pretty good. Maybe amazing, I don't know. So the file reputation in ScyllaDB part, this is the latency from Scylla monitoring directly in our production database system for 10 minutes, I think, or something like that. So we are, in average, under 6 milliseconds for writes, and under 1 millisecond for reads. Up there is write in the same scale. So the reads are very, very fast. It is 8-node cluster. So 99% latency is under 12 milliseconds, and reads are under 7 milliseconds. So it is almost 1 digit millisecond latency in general. So the lessons learned. How to save some precious NVMe disk space. Yeah, use and adjust your chunk size in a Scylla, and you can almost save with the LZ4 compression, almost half of the size you will have without compression. Repairs can impact cluster performance. They can. We tested that. It is not large, but we have an idea to have 1 digit millisecond response time, so we figure out how to tune that. And the latency on steroids means use NVMe disk, which is always mentioned in RAID 0 configuration, and it's great. It works fast and the best possible configuration right now. And that's it.